This video will be covering our nuclear charge and our shielding effect. First one that we're going to talk about is going to be our shielding effect. Now, our shielding effect is going to be our inner electrons, and they are going to essentially shield the valence electrons from the force of the nucleus. And our inner electrons are going to be our electrons that are not our valence. So kind of the easiest way to look at this visually is going to be with a Bohr model. So if we have our sodium atom, right, it has 11 protons in our nucleus. Our sodium atom also has 3 energy levels to it, so it's going to have 3 rings. Now, for this being a neutral atom, because it has 11 protons, it is also going to have 11 electrons. So 2 of those electrons are going to be in our first energy level, and then we're going to have 8 in our second energy level. Now, those 8 plus the 2 from the first energy level will be 10, leaving us only with 1 electron to place on our outermost ring. Right, so kind of big thing to remember here is that our outermost electron, this is going to be our valence electron. Everything else is going to be an inner electron. So all of those are going to be our inner electrons. So in our sodium atom, we are going to have 10 inner electrons and only 1 valence electron. Now, kind of an easy way to get our number of inner electrons really pretty quick is going to be our protons, or our total number of electrons, so in this case 11. We are going to subtract our 1 valence electron. So 11 minus 1, we get 10. So we are going to have 10 inner electrons. Now, our trend for our shielding effect is very straightforward on the periodic table. As we move down the periodic table, we are going to be increasing our shielding. So as our atoms get larger and larger, as we gain more energy levels, our shielding effect is going to increase. So we are increasing as we move down a group. Next, we're going to be talking about our nuclear charge. So our nuclear charge is going to be the overall charge of the nucleus of an atom. And this is going to be a very straightforward trend as well. As we move left to right across the periodic table, we are going to be increasing our nuclear charge. The reason that this is happening is because as we move left to right, we are going to be increasing the number of protons in that row. So looking at lithium versus beryllium. So lithium being Li, it has 3 protons. Our beryllium being Be has 4 protons. So as we move left to right, we are increasing our overall charge of our nucleus. So we are going to be increasing our nuclear charge. Now, along with that, instead of just having the trend, our nuclear charge also has more of a number behind it as well. And this is going to be called our effective nuclear charge. And our equation that we get is our Z effective. So our effective nuclear charge is equal to our Z minus our S. Our Z is going to be our number of protons in the nucleus, and our S is going to be our shielding constant. Now, our shielding constant for us, this is going to be our number of inner electrons. So our shielding constant is going to be our inner electrons that we have. Kind of our easiest way to really find our number of inner electrons is going to be our total electrons is going to be subtracted from our number of valence electrons. And that is going to equal out our number of inner electrons. So total electrons minus our valence electrons will equal our inner electrons. So let's go ahead and take a look at an example. In this case, our example is going to be, what is the effective nuclear charge of a sodium atom? So first thing we want to do is that we want to find sodium on our periodic table, and it is right here. It is going to be our atomic number 11, our Na. So our equation is going to be our effective nuclear charge All right, let's go ahead and take a look at our first example. So our first example asks, what is the effective nuclear charge of a sodium atom? So first thing we're going to do is that we are going to find our sodium on our periodic table, which is right here. It is going to be our Na, atomic number 11. Our equation, our Z effective, is equal to our Z minus our S. Our Z being our number of protons. So taking a look at our sodium, we're able to tell that it has 11 protons. Our S is going to be our shielding constant, or our number of inner electrons. So again, we are going to have our total electrons minus our valence electrons. And that will equal our number of inner electrons. So looking at sodium, our total number of valence electrons is 11. Our number of valence electrons will just be 1. So kind of a quick refresher going over our number of valence electrons. Column 1 has 1 valence electron. Column 2 has 2 valence electrons. Column 13 has 3 valence electrons. Column 14 has 4, and so forth. So sodium being in column 1 has 1 valence electron. So what we get is 11 total electrons minus our 1 valence electron, and that will equal our 10 inner electrons. So we are going to get 11 minus 10, which means that our effective nuclear charge of our sodium atom will be 1. And 1 will be our answer. All right, let's go ahead and take a look at another example. All right, our next example, it asks, what is the effective nuclear charge of a sulfur atom? So first thing we're going to do is find sulfur on our periodic table. It is atomic number 16, which will be our S. Our equation, our Z effective, is equal to our number of protons minus our shielding constant, or number of inner electrons. Looking at sulfur on the periodic table, we're able to tell that it has 16 protons to it. And now for our number of inner electrons. Again, we have our total electrons minus our valence electrons. And that will equal our number of inner electrons. So, with this being a neutral atom, we are going to have 16 total electrons. Because sulfur is in group 16, it is going to have 6 valence electrons. So what we're going to get is 16 minus 6, which means our number of inner electrons will be 10. So 16 minus 10, we will get an effective nuclear charge of 6. And that will be our answer. All right, let's go ahead and take a look at one more example. In this example, it is asking for the effective nuclear charge of a krypton atom. So first things first, we are going to find krypton on our periodic table, and it is right here. It is going to be atomic number 36 to the very far right. Our equation that we have, our Z effective, is equal to our number of protons minus our shielding constant. Looking at krypton, we have an atomic number of 36, so we are going to have 36 protons. To find our number of inner electrons, we have our total electrons minus our valence electrons, and that will equal our number of inner electrons. Being a neutral atom, krypton has 36 protons, so we'll also have 36 electrons. Krypton is in group 18, so it has 8 valence electrons, and so what we're going to get is 36 minus 8. And whenever we do that, we should get 28 inner electrons. So for our effective nuclear charge, it will be our 36 minus our 28, which will get us an effective nuclear charge of 8. And 8 will be our answer.